Results of the study. When pilots who had flown EFIS for several years were required to fly various maneuvers manually, the aircraft parameters and flight control inputs clearly showed some erosion of flying skills. During normal maneuvers, such as turns to headings without a flight director, the EFIS group exhibited somewhat greater deviations than the analog group. Most of the time, the deviations were within the practical test standards, PTS, but the pilots definitely did not keep on the localizer and glide slope as smoothly as the analog group. The differences in hand flying skills between the two groups became more significant during abnormal maneuvers such as slam dunks. When given close crossing restrictions, the analog crews were more adept at the mental math and usually maneuvered the aircraft in a smoother manner to make the restrictions. On the other hand, the EFIS crews tended to go heads down and tried to solve the crossing restriction on the FMS. Emergency maneuvers clearly broadened the difference in manual flying skills between the two groups. In general, the analog pilots tended to fly raw data, so when they were given an emergency such as an engine failure and were instructed to fly the maneuver without a flight director, they performed it expertly. By contrast, SOP for EFIS operations at the time was to use the flight director. When EFIS crews had their flight directors disabled, their eye scan again began a more erratic searching pattern, and their manual flying subsequently suffered. Equipment use. Autopilot systems. In a single pilot environment, an autopilot system like the one shown here can greatly reduce workload. As a result, the pilot is free to focus his or her attention on other flight deck duties. This can improve situational awareness and reduce the possibility of a CFIT accident. While the addition of an autopilot may certainly be considered a risk control measure, the real challenge comes in determining the impact of an inoperative unit. If the autopilot is known to be inoperative prior to departure, this may factor into the evaluation of other risks. For example, the pilot may be planning for a VHF omnidirectional range (VOR) approach down to minimums on a dark night into an unfamiliar airport. In such a case, the pilot may have been relying heavily on a functioning autopilot capable of flying a coupled approach. This would free the pilot to monitor aircraft performance. A malfunctioning autopilot could be the single factor that takes this from a medium to a serious risk. At this point, an alternative needs to be considered. On the other hand, if the autopilot were to fail at a critical, high workload portion of this same flight, the pilot must be prepared to take action. Instead of simply being an inconvenience, this could quickly turn into an emergency if not properly handled. The best way to ensure a pilot is prepared for such an event is to carefully study the issue prior to departure and determine well in advance how an autopilot failure is to be handled. Familiarity. As previously discussed, pilot familiarity with all equipment is critical in optimizing both safety and efficiency. If a pilot is unfamiliar with any aircraft systems, this will add to the workload and may contribute to a loss of situational awareness. This level of proficiency is critical and should be looked upon as a requirement, not unlike carrying an adequate supply of fuel. As a result, pilots should not look upon unfamiliarity with the aircraft and its systems as a risk control measure, but instead as a hazard with high-risk potential. Discipline is key to success. Respect for onboard systems. Automation can assist the pilot in many ways, but a thorough understanding of the systems in use is essential to gaining the benefits it can offer. Understanding leads to respect, which is achieved through discipline and the mastery of the onboard systems. It is important to fly the airplane using minimal information from the primary flight display, PFD. This includes turns, climbs, descents, and being able to fly approaches. Reinforcement of onboard suites. The use of an electronic flight display may not seem intuitive, but competency becomes better with understanding and practice. Computer-based software and incremental training help the pilot become comfortable with the onboard suites. Then the pilot needs to practice what was learned in order to gain experience. Reinforcement not only yields dividends in the use of automation, it also reduces workload significantly. Getting beyond rote workmanship. The key to working effectively with automation is getting beyond the sequential process of executing an action. If a pilot has to analyze what key to push next, or always uses the same sequence of keystrokes when others are available, he or she may be trapped in a rote process. This mechanical process indicates a shallow understanding of the system. Again, the desire is to become competent and know what to do without having to think about what keystroke is next. Operating the system with competency and comprehension benefits a pilot when situations become more diverse and tasks increase. Understanding the platform. Contrary to popular belief, flight in aircraft equipped with different electronic management suites requires the same attention as aircraft equipped with analog instrumentation and a conventional suite of avionics. The pilot should review and understand the different ways in which EFD are used in a particular aircraft. 2 simple rules for the use of an EFD. Be able to fly the aircraft to the standards in the PTS. Although this may seem insignificant, knowing how to fly the aircraft to a standard makes a pilot's airmanship smoother and allows him or her more time to attend to the system instead of managing multiple tasks. Read and understand the installed electronic flight systems manuals to include the use of the Autopilot and the other onboard electronic management tools. Managing aircraft automation. Before any pilot can master aircraft automation, he or she must first know how to fly the aircraft. Maneuvers training remains an important component of flight training because almost 40% of all GA accidents take place in the landing phase, one realm of flight that still does not involve programming a computer to execute. Another 15% of all GA accidents occurs during takeoff and initial climb. An advanced avionics safety issue identified by the FAA concerns pilots who apparently develop an unwanted over-reliance in their avionics and the aircraft, believing that the equipment will compensate for pilot shortcomings. Related to the over-reliance is the role of ADM, which is probably the most significant factor in the GA accident record of high-performance aircraft used for cross-country flight. The FAA Advanced Avionics Aircraft Safety Study found that poor decision-making seems to afflict new advanced avionics pilots at a rate higher than that of GA as a whole. The review of advanced avionics accidents cited in this study shows the majority are not caused by something directly related to the aircraft, but by the pilot's lack of experience and a chain of poor decisions. One consistent theme in many of the fatal accidents is continued VFR flight into IMC. Thus, pilot skills for normal and emergency operations hinge not only on mechanical manipulation of the stick and rudder, but also include the mental mastery of the EFD. 3 key flight management skills are needed to fly the advanced avionics safely: information, automation, and risk. Information management. For the newly transitioning pilot, the PFD, MFD, and the GPS VHF navigator screens seem to offer too much information presented in colorful menus and submenus. In fact, the pilot may be drowning in information, but unable to find a specific piece of information. It might be helpful to remember these systems are similar to computers, which store some folders on a desktop and some within a hierarchy. The first critical information management skill for flying with advanced avionics is to understand the system at a conceptual level. Remembering how the system is organized helps the pilot manage the available information. It is important to understand that learning knob and dial procedures is not enough. Learning more about how advanced avionics systems work leads to better memory for procedures and allows pilots to solve problems they have not seen before. There are also limits to understanding. It is generally impossible to understand all of the behaviors of a complex avionics system. Knowing to expect surprises and to continually learn new things is more effective than attempting to memorize mechanical manipulation of the knobs. Simulation software and books on the specific system used are of great value. The second critical information management skill is stop, look, and read. Pilots new to advanced avionics often become fixated on the knobs and try to memorize each and every sequence of button pushes, pulls, and turns. A far better strategy for accessing and managing the information available in advanced avionics computers is to stop, look, and read. Reading before pushing, pulling, or twisting can often save a pilot some trouble. Once behind the display screens on an advanced avionics aircraft, the pilot's goal is to meter, manage, and prioritize the information flow to accomplish specific tasks. Certificated flight instructors, CFIs, as well as pilots transitioning to advanced avionics, will find it helpful to corral the information flow. This is possible through such tactics as configuring the aspects of the PFD and MFD screens according to personal preferences. For example, most systems offer map orientation options that include north up, track up, DTK, desired track up, and heading up. Another tactic is to decide when possible how much or how little information to display. Pilots can also tailor the information displayed to suit the needs of a specific flight. Information flow can also be managed for a specific operation. The pilot has the ability to prioritize information for a timely display of exactly the information needed for any given flight operation. Examples of managing information display for a specific operation include program map scale settings for en route versus terminal area operation. Utilize the terrain awareness page on the MFD for a night or IMC flight in or near the mountains. Use the nearest airport's inset on the PFD at night or over inhospitable terrain. Program the weather data link set to show echoes and METAR status flags. Enhanced situational awareness. An advanced avionics aircraft offers increased safety with enhanced situational awareness. Although aircraft flight manuals, AFM, explicitly prohibit using the moving map, topography, terrain awareness, traffic, and weather data link displays as the primary data source, these tools nonetheless give the pilot unprecedented information for enhanced situational awareness. Without a well-planned information management strategy, these tools also make it easy for an unwary pilot to slide into the complacent role of passenger in command. Consider the pilot whose navigational information management strategy consists solely of following the magenta line on the moving map. He or she can easily fly into geographic or regulatory disaster if the straight-line GPS course goes through high terrain or prohibited airspace, or if the moving map display fails. A good strategy for maintaining situational awareness information management should include practices that help ensure that awareness is enhanced by the use of automation, not diminished. Two basic procedures are to always double-check the system and verbal callouts. At a minimum, ensure the presentation makes sense. Was the correct destination fed into the navigation system? Callouts, even for single-pilot operations, are an excellent way to maintain situational awareness as well as manage information. Automation management. Advanced avionics offer multiple levels of automation, from strictly manual flight to highly automated flight. No one level of automation is appropriate for all flight situations, but in order to avoid potentially dangerous distractions when flying with advanced avionics, the pilot must know how to manage the course deviation indicator, CDI, the navigation source, and the autopilot. It is important for a pilot to know the peculiarities of the particular automated system being used. This ensures that the pilot knows what to expect, how to monitor for proper operation, and promptly take appropriate action if the system does not perform as expected. For example, at the most basic level, managing the autopilot means knowing at all times which modes are engaged and which modes are armed to engage. The pilot needs to verify that armed functions, for example navigation tracking or altitude capture, engage at the appropriate time. Automation management is another good place to practice the call-out technique, especially after arming the system to make a change in course or altitude. In advanced avionics aircraft, proper automation management also requires a thorough understanding of how the autopilot interacts with the other systems. For example, with some autopilots, changing the navigation source on the EHSI from GPS to LOC or VOR while the autopilot is engaged in nav, course tracking mode, will cause the autopilot's nav mode to disengage. The autopilot's lateral control will default to roll, wing level, until the pilot takes action to re-engage the nav mode to track the desired navigation source. Risk management. Risk management is the last of the 3 flight management skills needed for mastery of the glass flight deck aircraft. The enhanced situational awareness and automation capabilities offered by a glass flight deck airplane vastly expand its safety and utility, especially for personal transportation use. At the same time, there is some risk that lighter workloads could lead to complacency. Humans are characteristically poor monitors of automated systems. When asked to passively monitor an automated system for faults, abnormalities, or other infrequent events, humans perform poorly. The more reliable the system, the poorer the human performance. For example, the pilot only monitors a backup alert system, rather than the situation that the alert system is designed to safeguard. It is a paradox of automation that technically advanced avionics can both increase and decrease pilot awareness. It is important to remember that electronic flight displays do not replace basic flight knowledge and skills. They are a tool for improving flight safety. Risk increases when the pilot believes the gadgets will compensate for lack of skill and knowledge. It is especially important to recognize there are limits to what the electronic systems in any light GA aircraft can do. Being PIC requires sound ADM, which sometimes means saying no to a flight. For the GA pilot transitioning to automated systems, it is helpful to note that all human activity involving technical devices entails some element of risk. Knowledge, experience, and mission requirements tilt the odds in favor of safe and successful flights. The advanced avionics aircraft offers many new capabilities and simplifies the basic flying tasks, but only if the pilot is properly trained and all the equipment is working as advertised. This chapter focused on helping the pilot improve his or her ADM skills, with the goal of mitigating the risk factors associated with flight in both classic and automated aircraft. In the end, the discussion is not so much about aircraft, but about the people who fly them. This concludes your introduction to aeronautical decision-making. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.